I first learned about the chaos game from my younger brother when he was attending Georgia Tech. From the time he told me about it, I wanted to write this program, and I wrote it for several different types of computers and for the calculator. The chaos game, you start with 3 points on a triangle, and then you randomly choose one of those corners. Well, I guess you first start at initial points anywhere on the screen, and then you randomly choose one of the corners and go halfway to the randomly chosen corners and draw another point. Then randomly choose another corner, or the same one, and go halfway between that corner and the second point you have. Then you have that gives you a third point. Then randomly choose another corner and go halfway there, and eventually you will get a picture of the chaos game. And most people speculate that you just get a series of dots all over the place, and everybody was pretty amazed when you get this Sierpinski's triangle, so we could start plotting those points. If you look closely, you can see that it's getting more and more intense as it picks new points, and every point is like if a point was there, the next point would be halfway to one of the corners randomly chosen. And this was really intriguing to me, and my first thought after I got that program written would be, see, here's the 1/2. What would happen if I did a square? So I decided that I would change the program. It wasn't this complicated at that point. What if I chose square 4, clear the screen, and do the same thing with 4 corners, and choose a point at random, go halfway there, and we start plotting points, and this is what happened. And I thought, oh, there's no pattern arriving. But I was wrong. It just looked like a nebula of points, which this is sort of what I expected with the rules from the triangle one. But my friend John Beckett had read an article in Scientific America, and he had seen in that article that somebody thought not of just going halfway to one of the corners, but making it a fractional distance, a different fraction. So if we go back to 3 and say, instead of going halfway there, let's go 2/3 of the way, and we start to a corner, start plotting points. Oh, we get this sort of Sierpinski triangle, but it's spread out more, and this center thing has expanded. And what if we went 3/4? I'm going to clear this, stop plotting the points and clear the screen. It goes further out. Well, Mr. Beckett, my friend John Beckett, had read in Scientific America that if we did the same thing with 4 sides, and instead of going the half, let's go back to 2/3 of the way to the corners, we actually get a visible pattern. Turns out to look like this Scottish plaid. And at that point, the question comes, what if you had more and more sides? What if you allowed the fractional distance to a corner to change? And what thus was born this program, which is called Fractal Madness or Fractal Explorer. And the kids seem to have a lot of fun with it. I enjoy working with it, and let's say we put it up to like 6 sides, and we go 2/3 of the way, clear the screen, start plotting points. We get this kind of figure formed. This is, you can see, I'll go through the directions of how to do this. The buttons are pretty self-explanatory. Start plotting points, stop plotting points, and clear the screen. Pretty straightforward. But before you start plotting them, you can set up the number of sides that you want. And I think I let this go from anywhere from number of sides from 3 to 25. I don't think I've ever actually done the 25, but I use the trig to locate the 25 points equally spaced around. We start plotting points. This does look a little bit like a nebula, but you'll start to see some definition in this configuration. And if we go further out, let's go out to 5. So if we go, say we take 8 sides and we say, like the original chaos game, go half of the way to one of the corners, again, you don't see too much definition. If you go halfway, sort of like a hole in the middle with 8 sides. And little hints of stuff, it's hard to see the pattern. But if we go further out, like 4/5, and we clear the screen, we start plotting points, we see that we get sort of this definition. You can see how to use the Fractal Madness. Before I close, I would like to say one thing else. There's another program that's out there written by Rick Paris, the late Rick Paris of Exeter Academy, and he has a program, and I will show you where to get that. I have a link from it on our website, and I'll show you where to get that now. If that's expired, you could probably write to me. I have his program on my machine, and he said that we could freely distribute it. He died, unfortunately, he died not too long ago, but his work is still wonderful. I wish I could write it. But since I can't, I'm so thankful that he's made it available to the public at large. I'll show you that in a minute. Bye. If you go to my website, howto.com, you'll see here favorite math links, and this is quite useful. And one of the links here, if you scroll down, is to Peanut software. It's there at this present time, and if you click on that, it says here by Rick Paris of Phillips Exeter Academy Math Department. And if we go there, I made a menu program for all of his programs so that you could remember what they are. His names are a little bit nerdy because he knows a lot about some of these topics, and he called his fractal program WinFeed, which I would have never guessed, but in my menu here I put what it's about. So you could download this menu program, but you could visit Exeter Academy and download his software. So he has these programs, and it's WinFeed, which is his Fractal Explorer, and I'll try to show you how that works. I've downloaded it before. To download it, you would just click this and it would download, and it will work on your Windows machine. I'm going to stop now and show you how his fractal program works. I don't understand it completely, but it's really well worth having if you are interested in the topics. He did a whole lot with the Mandelbrot set and the Julia set. I just did the chaos game, something I understood. But this is really a whole branch of mathematics, and it's very interesting. And it's good to let students explore with it, because some of them will be interested in the mathematics that evolves from it or devolves from it. Here you're looking at the window where I have downloaded Rick Paris's software. I chose the address down here. Here you've got each of his programs listed, but you can click down here and download the zipped file of all 9 programs. I suggest that you do that because they're all wonderful. And let's look at that program if I can. The default download is to a directory called Peanut on your C drive, and here we have WinFeed. Let's see if it can come up. It's this little window for WinFeed, and you choose the window and you can choose which family of fractals to study. So look at the Mandelbrot set. The way that this works is here's the Mandelbrot set, and you can click in, right mouse click, and it opens a new window to the place that you're exploring, so you can see the recursiveness of the Mandelbrot set. It's just beautiful, and I suggest, I have to keep pulling the window over. I hope you can see this. Isn't it beautiful? And I don't know how he programmed this. I wouldn't know where to begin, but I'm thankful that he did, and that he put it on a website where all the students and teachers can download it and look at the wonderful work. So I would suggest that you work with that program as well. Mine is a little more kindergarten-y, and you can work on the chaos game. Thanks. Have fun. It's a whole new topic of mathematics, and some people think it's the clue to how skin grafts can be done, or the growth of things at the molecular level. Who knows where it will lead? But it's well worth studying and beautiful to watch. Have fun. Bye.